All right, in this video, we're going to look at writing a series using sigma notation. So, in essence, working backwards from what we looked at in the last video. So, it can be time consuming to add a lot of terms of a series, especially if you have thousands on thousands of terms. It's way too much time to spend adding individual values to a running total. So, one strategy is to find a sequence rule for a given series and then evaluate it using a calculator. Most graphing calculators have the ability to find a series that you type into it. So, example 2, express each as a sum in sigma notation and then evaluate and round to 4 decimal places when necessary. So example 2a, we have 1 plus 3 plus 5 plus da 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 plus 987. Well, if we ignore the plus signs and just look at it in terms of the sequence values, we have 1, 3, 5, 7, 9, 11, 13, yada yada yada, all the way up to and including 987. So it is an arithmetic sequence that we're just adding the terms together. And we looked at in the sequence section how to find the rule for an arithmetic sequence. And the common difference is 2. And if we subtract 2 from our first term, we get our y-intercept of 1. So we can use the sequence 2n minus 1 to generate the terms 1, 3, 5, 7, yada, yada, yada. And from there, we can just add them. So what we're going to need now is the lower limit of summation, what's written below the sigma, and the upper limit of summation, what's written on above the sigma. And to get those two values, we're going to focus on this first value for the lower limit, and we're going to focus on this last value for the upper limit. So for our lower limit, what's going to go below sigma, if we take our sequence rule 2n minus 1 and set it equal to our first term, it's going to help us find what that lower limit's going to be. So add 1 and divide by 2, you get n equals 1. So our lower limit, we're going to start with n equals 1. And we can see that because if we plug a 1 in for n, 2 times 1 minus 1 is 1. And then the next one after 1 is 2. 2 times 2 minus 1 is 3, and et cetera, et cetera. To find the upper limit, we do the exact same thing, except we set our sequence rule, 2n minus 1, equal to the last term, 987. So adding 1 and dividing by 2, we get 494. So we have our sequence rule of 2n minus 1, our lower limit of 1, and our upper limit of 494. Here's how we can write this using sigma notation. Now from there, we can put this into a calculator and we'll get 244,036, which is a whole lot quicker than trying to manually add up 1 plus 3 plus 5 plus 7 all the way up to 987. So much, much quicker and more accurate to come up with a rule, sequence rule, a lower and an upper limit of summation, and then letting the calculator do what it's good at. All right, part B, we have 3, 9, 27, yada, 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 all the way up to 387,420,489. Yikes, that's a big number. Well, if we look at the terms 3, 9, 27, we do have a pattern in that it is a geometric sequence. So 3 times 3 to get 9, 9 times 3 to get 27, 27 times 3 to get 81. So it is a geometric sequence, which means our base is 3. And if we divide 3 by 3 to get our y-intercept, we get 1. So we have 1 times 3 to the n, or just 3 to the n. And now we can find the lower and upper limits by setting 3 to the n equals 3, and 3 to the n equals this giant 387 million plus number. So for our lower limit, set 3 to the n equals 3. This one probably don't need to really get logarithms involved, but you can use them if you like. You get n equals 1. For our upper limit, this is one where we have an exponential equation, so we're going to use logarithms. We take the log base 3 of both sides and use our power rule to bring down n, or we can again use the relationship that log base 3 of 3 to the n is just going to give us n. So, but you can always do this middle step. In any event, log base 3 of 387,420,489 is 18. So we have a sequence rule of 3 to the n with a lower limit of 1 and an upper limit of 18. Putting that into the calculator, we get 581,130,732. All right, part C, we have 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus would be a seventh minus an eighth, yada, 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 all the way up to plus 1 over 117. Now, with this particular problem, the terms don't form an arithmetic sequence, and they do not, and also they do not form a geometric sequence. So we're not going to be able to have those luxuries for this problem. So we're going to have to find a rule to come up with the values for this sequence. First, note that our signs are alternating between positive and negative. So we're going to have a -1 either to the n power or a -1 to, let's say, the n plus 1 power, because that'll generate positive and negative terms every step of the way. Notice also that we could write 1 as 1 over 1. If we did that, every single term would have a 1 in the numerator. And then your denominator starts at 1 and goes up to 117. So again, looking at it as 1 over 1, every term has a 1 in the numerator, which means our rule should have a 1 in the numerator. And then our denominator goes up by 1 every time. So I guess you could say the denominator is an arithmetic sequence. But here, we could try out the rule -1 to the n plus 1 over n. And if we start with n equals 1, we get -1 to the 1 plus 1 is, it simplifies to 1 over 1 will give us 1. Now, if we chose -1 to the n power instead, what we would find is that our first term would not be positive, it would be negative. So if you try it out, and with this one, it might take a little bit of work before you come up with this rule, but if you try it out and you don't get the right sign, but you get the right value, you don't have the right positive versus negative sign, then try maybe adding 1 to the exponent. That should help get the right sign to start. So our lower limit, n equals 1, which is nice because we can just look at the denominator. That makes it nice. Our upper limit is going to go to 117. So here's our sequence rule. -1 to the n plus 1 power over n. And then for sigma notation from 1 to 117, this is about 0.6974. So hardest part, again, is coming up with the sequence rules. Might have a little trial and error, but if you stick with it, you might find that you can get it quicker than you thought. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.